You've known their names for most of your life: Mercury, Venus, Earth, Mars. You learned them in order, maybe from a laminated poster taped to the wall of a fourth-grade classroom. Each planet drawn as a perfect circle, each one calm and harmless. It felt like the solar system was a tidy place. 4 rocky worlds lined up neatly under the sun, all following the same rules. But that was the simplified version, the one designed for memory and multiple choice tests. What no one told you was that one of these planets grows a tail hundreds of thousands of miles long. Another was once blue. Another almost drowned in runaway heat. And one, your own, survived only because of a string of cosmic accidents that could have easily gone the other way. If someone had told you back then that Mercury behaves like a comet, you wouldn't have believed them. But it does. It really does. Every moment of every day, the smallest planet in the solar system is blasted by the sun so violently that atoms stream off its surface and trail behind it in a glowing plume. You never saw that image in a textbook. You also never heard that a day on Mercury lasts longer than its whole year, or that if you stood on its surface, the sun might rise, stop, drift backwards, then move forward again. That alone is enough to make you look at Mercury differently. And then there's Venus, the bright evening star you've seen your whole life. In school, they called it Earth's twin. They meant well. Venus is almost the same size, almost the same mass, nearly the same gravity. But they didn't tell you what lies beneath those brilliant clouds, because words like crushed, melted, and destroyed don't fit well into a children's science chapter. Venus is hotter than a blast furnace. Its surface pressure is the same as being a full kilometer underwater. Its skies rain acid, and in the middle of all that destruction, the planet slowly rotates in the wrong direction, backwards, as if something enormous once hit it and turned its entire life upside down. You weren't told that Earth is the outlier, not the standard. Everything about your home planet is balanced on a razor-thin line. Its atmosphere, its distance from the sun, its protective magnetic field, its mix of gases, its temperature. Shift any one of these even slightly, and the world beneath your feet could have ended up like its siblings, scorched, suffocated, or frozen. No one tells kids that life is possible here because Earth has been lucky again and again. But as an adult, that kind of truth lands differently. It gives the world a soft glow of gratitude. And Mars, the quiet red world you grew up imagining as a dusty desert, was once far closer to Earth than you were told. There were rivers, real rivers, wide enough to carve valleys still visible today. There were lakes, maybe a northern ocean, rainstorms, clouds, and long seasons warmer than some winters on Earth. Mars was a world that nearly made it. It had almost everything it needed. Then its magnetic field died, its atmosphere thinned, and the cold crept in. You weren't told that Mars didn't fail because it was flawed. It failed because time ran out. These 4 rocky planets were born together from the same collapsing cloud of gas and dust. They formed in the same spinning disk around the same young sun. They began with the same raw ingredients, but they diverged into 4 completely different fates. One boiled, one baked, one balanced, one fated. That's the real story. Not the children's version. The adult version. the version shaped by heat and chance and billions of years of slow, relentless evolution. Tonight, as you settle in and your breathing steadies, you'll follow those worlds the way scientists understand them today. You'll see Mercury, stripped bare and glowing under the sun. You'll drift through the golden haze of Venus toward a surface so extreme it destroyed every machine we've ever sent. You'll look back at Earth with a new sense of how rare it is. And you'll walk the cold valleys of Mars, where ancient water once carved paths through stone. What they taught you in school was the outline. What you're about to hear is the real thing. 4 siblings shaped by the same parent star. 4 diverging paths. 4 lessons in how worlds survive, how they fail, and how fragile the line between them truly is. And this deeper version of the story begins with the eldest sibling, the one that wandered too close to the fire. When you picture Mercury, you probably imagine a small gray circle orbiting the sun like a quiet pebble on a string. But once you look closer, you see something far rougher, far darker, and far more battered than any classroom poster ever suggested. Mercury is tiny, yes, barely bigger than Earth's moon, but you feel the weight of its history the moment you imagine standing on its surface. The ground beneath you would be dark, ancient, and shredded by millions of craters, each one a scar from an age when the young solar system was a shooting gallery of rock and metal. Nothing here is smooth. Nothing here is gentle. You're looking at a world that has spent its entire existence absorbing everything the sun and space have thrown at it. Even its composition tells you something is different. While Earth is a mix of rock, water, iron, and silicates, Mercury is almost pure metal. Nearly 70% of its mass is iron, the highest metal content of any planet in the entire solar system. Its core is enormous, far larger in proportion than Earth's, as if the planet you see today is only the remaining heart of a world that once had more to it. You can't help but feel like Mercury is a survivor of something violent, as if much of its outer layers were stripped away long ago, leaving behind a dense metallic body almost as heavy, gram for gram, as Earth itself. For a planet so small, Mercury is surprisingly heavy in your mind, like a bruised fist of iron orbiting too close to a flame. The surface tells its own story. One of the most dramatic landmarks is a gigantic impact scar called the Tellurian Basin. If you could walk its rim, you'd be tracing the outline of a crater more than 1,000 miles wide. So enormous that the energy of the impact sent shock waves rippling across the entire planet. On the opposite side of Mercury, you find a region scientists call the weird terrain, a twisted landscape of disrupted hills and ridges believed to be the direct result of that ancient collision. Imagine being hit so hard that even the far side of your body cracks. That's Mercury. Around the Tellurian Basin and across much of the surface, you'd see vast plains of solidified lava. These smooth, dark fields are reminders of an early era when the planet was so hot and so fractured that molten rock flooded across the landscape. It's easy to look at Mercury now and think of it as a cold, dead world. But these frozen flows reveal a past filled with heat, movement, and eruption. And then there's the temperature. Mercury experiences the most brutal extremes in the solar system. During the day, surface temperatures climb above 400 degrees Celsius, hot enough to melt lead. But once night falls, Without an atmosphere to hold the heat, the temperature plummets below minus 170 degrees. The difference between blistering heat and bone-cracking cold happens over and over every single Mercury day. It's hard to imagine any surface surviving that kind of thermal whiplash without fracturing, twisting, and aging faster than worlds with gentler climates. Mercury's missing atmosphere is part of what makes these extremes so fierce. With its low gravity and constant exposure to the solar wind, the planet simply can't hold on to air. Anything that tries to cling to the surface gets blasted away by streams of charged particles flowing outward from the sun. Instead of a real atmosphere, Mercury has something closer to a ghostly veil, a thin exosphere made of scattered atoms that drift above the ground like dust floating in a vacuum. It's not air. It's the memory of air. And yet, even without a thick atmosphere, Mercury manages to produce one of the most unexpected features in the solar system: a tail. A real tail. Under the bright glare of the sun, sodium atoms are knocked off the planet's surface and pushed outward, forming a glowing plume that stretches hundreds of thousands of miles into space. Through certain telescopes, it looks like a comet's trail, a shimmering golden fan drifting silently behind a world made of metal. If someone had told you in school that the smallest planet grows a tail, you might have laughed. But here, in the calm of the night, that detail feels strangely fitting. Of course, Mercury has a tail. Of course, the planet standing closest to the sun leaves a stream of itself behind as it runs its endless orbit. This is the eldest sibling of the rocky planets, the one that stood too close to the fire and paid the price. While the others formed farther out, protected by distance or by luck, Mercury grew up in a place where the sun's heat, gravity, and radiation shaped everything about it. It lost its outer layers. It lost its air. It endured impacts that shook its entire body. It survived temperatures that swing hundreds of degrees in both directions. It became a world stripped raw, hardened, and exposed, yet still orbiting, still holding together, still carrying the evidence of its past on every square mile of its battered surface. As you picture Mercury hanging there in the harsh sunlight, you feel a strange mix of pity and respect. This is not the quiet, unremarkable rock you once imagined. This is a world that has taken every blow and kept moving. A world of metal veins, cracked skin, and ancient wounds. A world tough enough to orbit where almost nothing else could last. And the deeper you look, the more you realize that Mercury isn't just the first planet in line. It's the metal survivor of a violent childhood, and its story is only beginning to unfold. If you could stand on the scorched surface of Mercury long enough to watch the sky without melting or freezing, you would see something almost impossible. The sun would rise over the horizon like it does on Earth, climbing higher and higher. Then, without warning, it would slow down, pause, and begin to drift backwards. After a while, it would stop again, turn around, and continue its climb as if nothing strange had happened. It's the kind of sight that would make you question your own senses, because your instincts are shaped by Earth, by a world where the sun follows reliable paths. But Mercury does not play by Earth's rules. Its sky bends the logic you've carried your whole life. This strange motion begins with Mercury's orbit, the most stretched and lopsided of the 4 rocky planets. Instead of gliding around the sun in a neat circle, Mercury moves on an ellipse so elongated that its distance from the Sun changes dramatically as it travels. When it's closest, sunlight hits the surface with more than twice the intensity it feels when Mercury is farthest away. The brightness of the daylight changes so drastically from point to point that the planet looks like it is breathing, swelling with light, then relaxing into shadow. But the real heart of the weirdness lies in the way Mercury rotates. Most planets have a simple rhythm, a set number of hours in a day, a predictable spin, a comfortable pattern. Mercury does something else entirely. It's locked in a 3-to-2 resonance with the Sun, meaning that for every 3 times it spins around its axis, it only completes 2 orbits around the Sun. That alone is enough to make the sky behave strangely, but the effect gets even more dramatic when you combine it with the planet's stretched out orbit. Because of this perfect and unusual resonance, Mercury's solar day, the time from one noon to the next, is about 176 Earth days long. That means that one single sunrise to sunrise cycle lasts longer than Mercury's entire year, which is only 88 days. It's a world where years fly by quickly, while days crawl forward with excruciating slowness. If you lived there, you'd celebrate New Year's Day twice before seeing the sun return to the same point in the sky. This unusual timing creates the sunrise reversal, the moment when the sun appears to stop, drift backward, and then continue forward again. It's one of those rare cosmic behaviors that feels like the universe is bending its own rules. Because the combination of Mercury's spin and orbit creates a moment when its rotation briefly fails to keep up with its orbital motion. To your eyes, it looks like the Sun has changed its mind. Mercury keeps adding to its collection of strange qualities with something that seems almost contradictory. For all its heat and wild temperature swings, the planet barely has seasons. Its tilt is almost zero, so small that the planet's axis is nearly upright compared to its orbit. This means Mercury doesn't lean toward or away from the Sun like Earth does, so it doesn't experience the shifting sunlight patterns that create the familiar transitions between winter and summer. But even without seasons, there are places on Mercury where sunlight never reaches. At the poles, inside deep craters with walls tall enough to block the sun permanently, lie regions of eternal darkness. These pits are so cold and so deeply shadowed that temperatures drop low enough for something completely unexpected on the hottest planet in the solar system. Ice. Real, solid, water ice. Spacecraft confirmed it. The Messenger mission, orbiting Mercury and mapping its surface, detected reflective patches in these craters that match the signature of frozen water. It seems impossible at first. How can there be ice on a world where the surface temperature can exceed 400 degrees Celsius? But the geometry explains it. The sun never climbs high enough to illuminate the crater floors. The shadows are so long, so deep, and so permanent that they trap cold the way a cave might trap echoes. Ice can survive there for millions of years without melting, even while the surrounding rocks bake under a sun 10 times brighter than Earth's. Discoveries like this force you to rewrite your expectations. You grow up learning that heat and cold follow simple patterns, that worlds close to the sun are dry and worlds far away are frozen. Mercury breaks that logic. It shows you that even in a place of violent heat, there can be pockets of deep freeze if the angles are just right. And that realization cracks open a much bigger idea. Stability isn't always about distance. Sometimes it's about geometry, shelter, and shadows. The more you think about Mercury's orbit, the less it feels like a normal planet, and the more it feels like some strange clockwork experiment, a machine built from gravity, heat, and chance. Its days stretch longer than its years. Its sun turns around in the sky. Its seasons barely exist. Its coldest places lie in permanent night, only a few hundred miles from landscapes hot enough to liquefy metal. It is a world that obeys a set of rules Earth never had to learn. Rules written by proximity to the sun. By the time you step back from this picture, the message is clear. Mercury isn't just strange on the surface. It's strange in the way it moves. Strange in the way it spins. Strange in the way it splits heat and cold. And strange in the quiet persistence of ice hidden inside darkness. Nothing about it aligns with the simple diagrams you once memorized. And everything about it reminds you that the solar system is broader, wilder, and more flexible than earthbound logic allows. On Mercury, even the sun can stop and change its mind. If you imagine sending a spacecraft toward Mercury, you might picture something simple. After all, Mercury is close. It's the first planet, the nearest neighbor to the sun. You might think the journey is as straightforward as pointing a spacecraft inward and firing the engines until you arrive. But in reality, going inward is harder than going outward. Leaving the inner solar system is like walking up a long, gentle hill. You're moving away from the sun's gravity, and although the climb is steady, you're fighting a pull that weakens with every step. But heading toward the sun is the opposite. It's like sliding down a steep well, picking up speed whether you want to or not. Every mile you descend pulls you faster, and every inch closer demands more and more energy if you want to hit the brakes. This is the central challenge. The sun doesn't just sit there glowing. It drags everything toward it with relentless force. As a spacecraft drops inward, it accelerates continuously, pulled by gravity into a faster and tighter fall. To enter orbit around Mercury, you don't just need to arrive. You need to slow down dramatically. You have to remove an enormous amount of speed, far more than you'd ever expect for such a small planet. In fact, the fuel required to break into Mercury orbit is so huge that if you tried to carry it all at launch, the spacecraft would be too heavy to lift off in the first place. Because of this, for decades, scientists avoided trying to orbit Mercury at all. They flew past it instead. It was simpler, safer, and far more achievable. In the mid-1970s, NASA's Mariner 10 flew by Mercury 3 times, each pass carefully angled to reveal a little more of the surface. Even so, the mission only managed to photograph about 45% of the planet. Yet those partial views were treated as a triumph, because at the time, a full orbit seemed almost impossible. But then came an engineer named Qinhuang Yan, working at the Jet Propulsion Laboratory. While others were focused on solving the fuel problem, he approached Mercury from a different angle. Instead of burning fuel to slow down, he wondered if gravity itself could do the braking. And that idea changed everything. Picture the solar system as a dance floor. Rather than flying straight at Mercury, Yen proposed sending a spacecraft on a long looping path that used the gravity of other planets to gradually remove speed. This maneuver, called a gravity assist, lets a spacecraft steal a bit of momentum from a world as it passes by, changing course while shedding or gaining velocity without using fuel. Yen's plan involved not just one assist, but a chain of them. First Earth, then Venus again, then Mercury again. Each flyby shaving off a little more speed, each loop drawing the spacecraft closer to the Sun without letting it fall uncontrollably into the star's gravity well. Imagine riding a carousel around the Sun, circling wider and wider paths that draw you inward instead of outward. Every pass past a planet slows you down just enough so that eventually, after billions of miles, the speed you've lost is enough to allow Mercury's tiny gravity to catch you. It's an elegant solution, but it's also unforgiving. A gravity assist chain has to be calculated with almost perfect precision. Arrive a few minutes early or a few minutes late at any stage, and the entire sequence collapses. What should have been a gentle handoff becomes a slingshot into empty space. To reach Mercury, using this gravitational choreography, the spacecraft must travel 6 or 7 years, looping around the inner solar system in a journey that covers more than 6 billion kilometers. By the time you imagine the path it takes, you stop thinking of Mercury as a small, simple world and start respecting the sheer difficulty of reaching it. The planet isn't just close to the Sun. It's trapped in a region where speed becomes a punishment, not an advantage. And only the patience of gravity can guide you safely toward it. It's counterintuitive, almost backward, that traveling to the closest planet requires a path more complicated than missions sent to Jupiter or Saturn. But that's part of the truth the solar system hides behind its simple diagrams. When you move inward, you aren't approaching a quiet world. You're approaching the engine room of the entire system, a place where gravity tightens, where heat intensifies, and where every orbit grows sharper and less forgiving. So when you think about what it takes to explore Mercury, you begin to appreciate why it remained mysterious for so long. You couldn't just go there. You had to sneak up on it, circling through space again and again until the Sun's pull weakened just enough for a delicate insertion into orbit. By the time a spacecraft finally arrives, the journey has already endured more complexity, more corrections, and more careful planning than nearly any other planetary mission. To reach Mercury, you don't aim straight for it. You dance around the Sun until gravity finally lets you slow down. And so, after 6.5 billion kilometers, one spacecraft finally made it. By the time a spacecraft finally reached Mercury's orbit in 2011, it felt less like an arrival and more like the end of a pilgrimage. The spacecraft was called Messenger, short for Mercury surface, space environment, geochemistry, and ranging. And it carried with it decades of questions. For generations, Mercury had been the loneliest, least known of the rocky planets. It was too close to the Sun for easy photography, too difficult to reach, too expensive to orbit. But Messenger changed that. After a 6.5-year journey that looped around the Sun 15 times and executed a chain of gravity assists that looked like something a mathematician dreamed on a sleepless night, the spacecraft slid into Mercury's orbit and opened the curtains on a world we had only glimpsed from afar. From its first weeks in orbit, Messenger began scanning the entire surface, photographing the craters, the plains, the cliffs, and the strange geological scars that stretched for hundreds of kilometers. It didn't just capture snapshots, it built the first complete map of Mercury. Radar measurements revealed elevations and ridges in fine detail, creating a topographic portrait of the smallest planet with a clarity no one expected. The world that once appeared as a bright dot in the sky now lay exposed in sharp definition, every valley and fracture illuminated, and the discoveries began almost immediately. The first major surprise: Mercury has a magnetic field. Not as strong as Earth's, only about 1%, but unmistakably real. Magnetic fields don't appear out of nowhere. They need movement, heat, fluidity. That meant something inside Mercury was still alive. Its core wasn't a solid iron lump frozen in time. It was molten. It was stirring. It was powering a weak but persistent magnetic shield around a world no one expected to have one. Then came the next discovery. Mercury's core was enormous, far larger in proportion than that of any other rocky planet. In fact, more than half of Mercury's interior is molten metal. The crust and mantle, the rocky shell that makes up most of Earth, are thin layers wrapped around this vast iron heart. Why would a planet so small have a core so big? The leading idea is that Mercury was struck by something huge in its youth. An impact so violent it blasted away much of its outer rock, leaving behind the heavy metallic interior. Messenger's measurements strengthened this idea by showing just how oversized that core truly is. But the surprises didn't stop. Messenger also confirmed the presence of water ice at the poles. Real, solid ice, hidden inside craters where sunlight never reaches. The bright reflections spotted by telescopes on Earth were right. Neutron measurements told the same story. This was frozen water mixed with frozen organic material on the hottest planet in the solar system, where daytime temperatures can melt steel. There are pockets of ice so cold and so stable that they've survived for millions of years. It was one of the most unexpected findings in planetary science, a reminder that shadows can be stronger than heat. Then Messenger found evidence that Mercury is shrinking. Across the surface, the spacecraft mapped enormous cliffs called lobate scarps, long curved ridges that run for hundreds of kilometers. These cliffs are signs of a cooling planet. As Mercury's interior slowly loses heat, the whole world contracts, wrinkling like the skin of a drying apple. From the patterns of these scarps, Messenger scientists estimated that Mercury's diameter has shrunk by more than 14 kilometers over its lifetime. That's not something you see on Earth or Mars. This is a world literally tightening itself over billions of years. Messenger also detected something even stranger. Mercury contains high levels of volatile elements like potassium, sodium, and sulfur, materials that should have evaporated if the planet had ever been heated enough to lose its outer layers. Their presence challenges long-standing theories of how Mercury formed. Either the impact that stripped away its crust wasn't as hot as expected, or Mercury's early environment preserved these elements in ways we still don't fully understand. Whatever the explanation, it forced scientists to rethink the story of the innermost planet's birth. And then came perhaps the most visually striking discovery of all: the hollows. These shallow, irregular depressions scattered across the surface were unlike anything seen on any other planet or moon. They were bright, young, and surprisingly fresh-looking, suggesting they are geologically recent, possibly still forming today. Scientists think they may be created when volatile materials near the surface evaporate directly into space, leaving behind gaps and collapsed pockets in the ground. Mercury, once thought to be a dead, silent world, was showing signs of ongoing activity. Messenger revealed more than photographs. It revealed personality, a world of metal plains where frozen lava stretches like ocean floors, a world where ice sleeps inside shadows and where cliffs rise like the wrinkles of an aging giant, a world that still shifts, still changes, still breathes in its own way. It showed a Mercury with a magnetic pulse, a molten interior, a geologic past full of fire, and a present shaped by evaporation, contraction, and relentless sunlight. Images of the hollows glowed with delicate colors. Maps of the magnetic field revealed a dipole shifted northward, hinting at strange flows inside the core. Infrared data traced patches of heat that didn't match the craters above them. Mercury wasn't simple. It wasn't just a rock. It was a world still writing its own story. Messenger didn't just map Mercury. It rewrote what we thought a small planet could be. Every time we looked at Mercury, it surprised us again. And to understand why this planet looks the way it does today, you must first understand what it was before it cooled. Imagine Mercury not as the dark, cratered world you know today, but as a glowing ember, a planet half melted under a young and furious sun. In the earliest chapters of the solar system, the sun wasn't the steady golden star you see now. It was wild, unstable, blasting radiation outward in violent waves. Flares snapped like whips. Solar winds roared with a force far beyond anything Earth experiences today. And Mercury, the closest world, lived inside that furnace. It received more than 7 times the intensity of sunlight that reaches Earth. That kind of heat doesn't just warm rock, it transforms it. In those early ages, Mercury's surface wasn't solid, it was molten. The ground shimmered like liquid metal. The crust sagged and bubbled under the weight of magma oceans that stretched for hundreds of miles. If you could have hovered above the young planet, you would have seen vast sheets of glowing orange lava rippling and flowing beneath a sky so black it made the molten surface look brighter still. Impact craters didn't stay craters for long. The moment something slammed into Mercury, lava rushed up from below to fill the hole, smoothing the surface like spilled paint. Messenger's images confirmed what models had predicted for decades. Mercury once flowed. The evidence sits everywhere. You see it in the broad basalt plains, called smooth plains, that cover surprisingly large areas of the surface. These plains share the same texture and reflectivity you see on volcanic flood basalts on Earth. The kind that come from massive eruptions, not small lava fountains. The resemblance is unmistakable. You also see the story in the shapes of Mercury's lava flows. Some look like pancakes, thick, rounded mounds formed when lava pooled and spread before cooling. Others appear as long, sinuous valleys carved by rivers of molten rock, frozen mid-motion. These channels, similar to the lunar Valles systems, trace the paths of ancient lava rivers that once rushed across the landscape. They're reminders that Mercury wasn't just hot. It was volcanic on a scale we rarely associate with such a small world. Then there are the calderas, massive volcanic depressions that point to what may have been supervolcanoes. On Earth, a supervolcano represents an eruption powerful enough to reshape regions and climates. On Mercury, such eruptions would have poured out enormous volumes of magma, covering craters, drowning valleys, and thickening the crust in layers upon layers of molten rock. These structures aren't speculative. They're visible. You can see their circular outlines, their collapsed centers, the patterns of lava that once radiated outward. Mercury was reshaped by eruptions big enough to rewrite continents, if it had ever had continents at all. If you close your eyes for a moment and let the imagery settle, you might imagine Mercury as it once looked, a world glowing like heated steel, the surface shifting and heaving under a mantle of liquid rock. The sky would be dark even as the horizon blazed. The edges of the planet would radiate with red heat. Waves of molten material would rise and fall as if the entire crust breathed fire. It's a vision, both violent and strangely serene, where the only sound is the slow, heavy movement of magma under the weight of the sun's early glare. Over time, the world cooled. The lava hardened. The magma beneath retreated, leaving behind depressions, fractures, and collapsed basins where the molten interior once pushed upward. The solid shell contracted as the heat escaped into space, and the surface wrinkled into long scarps that still cut across the land billions of years later. When you look at Mercury today, its cliffs, its cracked plains, its smooth basalt floors, you're seeing the shapes left behind by that cooling. The world that once flowed eventually stiffened into the metal-rich planet we observe now. Earth, too, had its own magma ocean in its infancy. Every rocky planet did. But Mercury's version was more extreme, more prolonged, more exposed. Earth cooled into oceans and continents. Mercury cooled into metal, rock, and scars. Where Earth found a path toward life, Mercury found a path toward survival. That difference is part of the story that defines the four Tellurian siblings. Born from the same fire, they diverged almost immediately by distance, heat, and fate. And Mercury, the eldest, survived the fire first. In a very real sense, the planet we see today is the cooled skeleton of a world that once glowed like the surface of a star. Its plains are the frozen remnants of ancient seas. Its valleys once carried rivers of molten stone. Its cauldrons once roared with eruptions you could see from space. The quiet gray crust hides a history of heat so intense it reshaped the entire surface again and again. Before Mercury cooled into metal and dust, it flowed. And in the next chapter of its story, those ancient eruptions left behind a surface cracked, shattered, and scarred in ways no other planet shares. If you look at Mercury from orbit long enough, you start to feel as if you're staring at a shattered object, like holding a piece of cracked glass under a desk lamp. Light catches the fractures. Shadows exaggerate the edges. Every angle reveals a new line, a new mark, a new disturbance written across the surface. Mercury isn't smooth. It isn't gentle. It looks like a world that has spent billions of years absorbing impacts, shrinking, twisting, and warping under forces that would have broken anything less resilient. One of the first things that draws your eye are the rays, long, bright streaks that shoot outward from certain impact craters like starbursts. On Earth's moon, rays are striking enough, But Mercury's are something else entirely. Some stretch hundreds of kilometers across the surface. Others span nearly 1,000. They radiate in all directions from the site of the collision, thin and delicate at the edges, but brilliant at their core. These rays form when material from an impact is thrown outward at high speed, scattering across the landscape in lines that stay bright, because Mercury's thin exosphere cannot erode them. Laboratory experiments have shown something unexpected. The length and clarity of these rays depend less on the speed of the impact and more on the texture of the ground they strike. A rougher, older surface produces softer, more broken patterns. A smoother one produces long, clean streaks that shine like scratches on polished metal. Mercury, with its ancient lava plains and its relatively young resurfaced areas, creates some of the most dramatic rays in the solar system. The crater Hokusai is one of the best examples. From high above, it looks like a bright explosion frozen in time, its rays stretching so far that they wrap around parts of the planet. Under the right lighting, Hokusai's rays appear like white brushstrokes painted across a dark canvas, sharp enough that you can trace them from orbit without losing the thread. No one expected a tiny planet scorched by the sun to have features this bold. Yet here they are, shimmering like light trapped in stone. But Mercury's mysteries run deeper than surface streaks. The planet is covered with enormous fractures called lobate scarps, evidence of a world that is literally shrinking as it cools. These cliffs rise like wrinkles across the crust, some extending for hundreds of kilometers. They cut through craters, through plains, through any terrain unlucky enough to lie in their path. Picture the crust tightening around the cooling interior, like a metal plate contracting as it loses heat, folding in on itself until breaks form. Mercury is still carrying those scars. And then there are the chaotic terrains, regions that look as if the ground has slumped, twisted, or buckled randomly. Hills tilt in unnatural directions. Blocks of crust pile up like rubble. Scientists once thought these areas were created solely by ancient impacts, but MESSENGER revealed that some chaotic terrains sit opposite major craters, as if shock waves rippled through the entire planet and shredded the surface on the far side. It's like seeing bruises on the back of a hand caused by a blow to the front. But the strangest structure of all, the one that turns Mercury's surface into a kind of cosmic crime scene, is Pantheon Fossae. You could spend hours looking at it and still not fully grasp what you're seeing. More than 1,000 radial troughs stretch outward from a central point, like the beams of a shattered window or the strands of a stone spiderweb. This isn't one or two cracks. It's an entire network of rifts arranged with unsettling precision. From above, it almost looks engineered, though it is unquestionably natural. At the heart of this sprawling pattern sits Apollodorus crater, a nearly circular depression perfectly positioned at the center of Pantheon Fossae. The alignment is so exact, so mathematically clean, that it almost feels staged. Did the impact that created Apollodorus also cause the radiating troughs? Or did the troughs already exist, and the crater just happened to land in the middle? The odds of such a coincidence seem tiny, and yet the evidence doesn't fully support either explanation. Some scientists argue that the crater is too young to have caused the entire network. Others think the impact's shock waves could have fractured the crust outward. Messenger gathered every detail it could, but the planet stayed quiet. Pantheon Fosse never confessed. Years later, the debate continues, and the feature remains one of the most enigmatic geological patterns in the solar system. As planetary scientist Thomas Waters put it, Pantheon Fosse is one of the strangest geological features in the solar system. And when you look at it long enough, you understand exactly why he said that. By the time you pull back from Mercury's surface, the impression is overwhelming. This world is warped and cracked. It has been stretched, shrunk, struck, melted, refrozen, and shattered countless times. It carries its history openly, etched into every ridge, every ray, every fractured plane. Mercury isn't just a small planet. It's a survivor that looks as though it has been hammered for billions of years without ever being given a moment to heal. Pantheon Fosse looks like someone tapped Mercury with a cosmic hammer and left it fractured. But Mercury's mysteries are only the beginning. The next planet isn't just cracked, it's cursed. You've just walked across a world that feels less like a planet and more like a record of everything the early solar system could throw at it. Mercury, the eldest sibling, took the fire first. Metal at its core, oceans of molten rock in its past, a surface cracked and folded from cooling, a comet-like tail torn from its skin, and mysteries carved into stone like fingerprints left at an ancient crime scene. Everything about Mercury whispers the same truth. This was the child closest to the storm. And when we began this journey together, you heard a promise. What they didn't teach you in school. Mercury delivered on that promise. It wasn't the quiet gray dot you memorized in childhood. It was complex, beaten, melted, fractured, and astonishingly alive in its own harsh way. In every family, one sibling takes the brunt of the storm. In the family of the Tellurian planets, that was Mercury. It stood closest to the sun, endured the heat, survived the collisions, and carried the earliest scars. But the story of 4 rocky worlds isn't about one survivor. It's about the ways 4 siblings, born from the same disk of dust and fire, grew into 4 radically different destinies. And the second sibling, the one next in line, is nothing like the first. If Mercury is the raw metal forged in the furnace, Venus is the mirror that misleads you. At first glance, Venus looks familiar, almost reassuring. Same size as Earth, nearly the same mass, nearly the same density. For a moment, if you blur your eyes, the 2 worlds could pass as twins. That resemblance is why Venus has always held a certain romantic charm. The bright evening star, the morning star, the planet that shines more brilliantly than anything else in the night sky except the moon. But as the pace slows and you drift toward it, a different truth begins to settle in. Venus may look like Earth from afar, but it diverged in a way that rewrote its destiny. Instead of cooling gently like its siblings, Venus fell into a runaway greenhouse effect that turned a once Earth-like world into a crushing furnace. The shift wasn't subtle. Venus became hotter than Mercury. Even though Mercury is closer to the sun, Venus became denser, heavier, more oppressive. Its skies thickened into a smothering blanket of carbon dioxide. Its clouds turned into sulfuric acid. The surface pressure grew so intense it could crush a submarine. 2 siblings, born almost the same size, yet separated by fate. As you drift deeper into this transition, the mood softens. Mercury's violent history fades behind you, and Venus begins to glow ahead, bright, deceptive, and beautiful in a way that hides the catastrophe inside. It is the planet that looked the most like Earth and ended up the farthest from it. And that contrast is what makes Venus important. Venus is a warning written in the sky, a reminder of how fragile balance can be, a glimpse of how quickly a world can slip into a place where life is no longer possible. You don't need to exaggerate Venus to make it dramatic. Science already did that. So take a breath. Slow your thoughts. Let the brightness of Venus drift closer in your imagination. We're leaving a world shaped by fire and entering one shaped by atmosphere. A world not just hot, but hostile in a way almost nothing else in the solar system can match. Let's descend toward the brightest world in our sky. This is Venus, the sister that looked like Earth, until she didn't. When you see Venus in the night sky, it looks peaceful. Just a bright, steady beacon hanging above the horizon. Soft, elegant, almost gentle. It's the brightest object in the night sky after the moon, glowing with a clarity that has inspired thousands of years of poetry, navigation, and myth. But the radiance you see from Earth is a lie of reflection. Venus shines not because it is kind, but because its clouds are so intensely reflective that they bounce sunlight back into space like a cosmic mirror. Those clouds, bright as they are made of sulfuric acid, beauty-hiding corrosion, light-hiding suffering. Venus is almost Earth's twin in the simplest numerical ways. It is about the same size. Its gravity is about 90% of Earth's. Its bulk composition is similar. For millions of years of astronomy, Venus was assumed to be a sibling so close that maybe the two planets once shared early oceans, early storms, and early climates. But that is where the resemblance ends, sharply and permanently. Once you begin to descend toward the planet, its true nature reveals itself. The atmosphere is a crushing weight, 92 bar of pressure at the surface. That's the equivalent of standing a full kilometer beneath the ocean on Earth. Imagine the weight of that water pressing in from all directions. That's Venus's air. You couldn't survive 1 second without being crushed. And the air isn't really air at all. It's mostly carbon dioxide, 96% of it, mixed with nitrogen and trace gases that sting the imagination. Sulfur dioxide, carbon monoxide, chlorine compounds. Above you, the clouds thicken into immense layers of sulfuric acid droplets, wrapped around the planet like a cocoon of toxic fog. Each part of the sky is brighter than Earth's clouds, but heavier, more smothering, more dangerous. Then there is the heat. Venus's surface reaches temperatures around 460 degrees Celsius, hotter than Mercury, even though Venus is nearly twice as far from the Sun. The reason is the runaway greenhouse effect, the most extreme example we know of. On Earth, if our global temperature rises by a single degree, governments issue reports. On Venus, the temperature didn't rise by a degree. It rose by hundreds. The thick blanket of carbon dioxide trapped heat so effectively that the planet's surface essentially lost its ability to cool. It baked. It scorched. It reached a thermal point of no return. This runaway cycle didn't happen overnight. It grew slowly from small changes in sunlight absorption, from clouds that thickened, from volcanic gases that darkened the sky, from oceans that may have evaporated into steam and disappeared. One shift led to another. Each feedback loop fed the next. Venus didn't just heat up. It fell into a spiral that redefined it forever. If you could stand on the surface, protected by impossible technology, you would see a world of vast volcanic plains. 80% of the surface, mapped in exquisite detail by NASA's Magellan mission, is covered in lava flows that once surged across the terrain in waves. Immense shield volcanoes rise from the plains, some so wide they dwarf Olympus Mons on Mars. Ridges, plateaus, and tessera terrain, wrinkled, folded highlands, fill the gaps between the plains like pieces of a broken continent. Scientists believe Venus may have experienced something unprecedented: global resurfacing, a time when the entire crust melted or destabilized, erasing nearly all craters and leaving a young surface despite the planet's ancient age. Imagine a world so volatile that it periodically wipes its own geological history clean. That is Venus, and the oddities continue. Venus spins backward. While Earth and most planets rotate counterclockwise, if viewed from above, Venus rotates clockwise, retrograde. Its day is longer than its year. One Venusian day lasts 243 Earth days, while a Venusian year lasts just 225. The surface experiences morning and evening in slow, suffocating motion, with sunlight filtering through yellow haze that barely reaches the ground. Why does Venus spin backward? There are theories. A colossal impact early in its history. Atmospheric tides that drag the planet into a new rotation. Or perhaps Venus once spun normally, but slowed and flipped due to long-term instabilities. Whatever the cause, the end result is a planet moving against the rhythm of the solar system, as if rejecting the direction its siblings took. And strangely, for all its violent heat and pressure, Venus is almost silent. Winds at the surface are slow, barely walking speed. The air is too dense to allow fast winds. It's like trying to stir molasses. The planet radiates with heat, but whispers with motion. You could stand there and witness an inferno that barely moves. So much of Venus is contradiction. The brightest world is the darkest. The sister planet is the opposite of Earth. The most Earth-like is also the most hostile. If you ever wondered what a runaway greenhouse looks like, look up at the evening star. It's there every night, shining like a jewel carved from light, while hiding a landscape that would destroy anything human-made in minutes. Venus is awe wrapped in caution, beauty wrapped in warning. And its story isn't finished yet. Because the most revealing truth about Venus isn't in the way it looks from orbit, or the way it glows from a backyard telescope, but in what lies beneath those clouds. But to understand Venus, we have to fall through the clouds. Let's fall, not quickly, not violently, but in a slow, drifting descent, like lowering yourself into a dream you can't quite predict. Above the clouds of Venus, the air is surprisingly cold. The winds here race around the planet at hurricane speeds, carrying particles of sulfuric acid in their spray. From far above, this layer feels thin and light, almost gentle. It's easy to forget, for a moment, what waits below. But as we descend, the world thickens. The droplets of sulfuric acid gather. The haze becomes denser, turning from pale yellow to deep amber. Light scatters strangely here. Everything feels dim, distorted, as if we're falling through the smoke of a distant fire. The beauty is undeniable, but so is the weight gathering around us. Pressure builds fast. With every kilometer, it's like sinking deeper into an ocean you can't see. The atmosphere stops behaving like air and starts behaving like something else. Supercritical carbon dioxide, a state where gas acts like liquid and liquid like gas. It swirls, presses, and clings with a heaviness no human has ever physically felt. You don't breathe this air. You endure it. The heat rises too, quietly but relentlessly. At first it's warm, then it's stifling, then it's unbearable, like standing near the open door of a metal furnace. The deeper we fall, the more the temperature climbs toward 300 degrees, then 400, then higher still, until no part of our imagination can pretend this is survivable. Through the thickening clouds, the surface begins to appear, just barely. A muted glow, a hint of shape. It's close, but still veiled in the heavy golden mist. And somewhere, faint but unmistakable, a crackling sound echoes, a fragmented radio signal, the same kind that once carried the voices of the Venera landers, machines that braved this descent for real. Those landers were not built to survive. They were built to endure for as long as possible before inevitable failure. Venera 13 lasted 127 minutes, a record on Venus. Venera 14 lasted 57. Others managed only seconds before the planet crushed them, melted them, or crippled their instruments. The descent was brutal. The landing was worse. But every minute they lived, they sent home something priceless. Postcards from hell. As we fall deeper, imagine sitting inside one of those landers. The shaking, the heat, the pressure closing in like the weight of a collapsing mountain. The outer shell creaking as metals soften. The cameras struggling to adjust to the yellow-orange haze. The microphones catching only the faint hiss of winds too sluggish to whistle. Then the lens opens, and we see it. Not fiction, not an artist's rendering. The real surface of Venus. Desolate stones the color of burnt ochre. Flat slabs of cracked rock. Basaltic, ancient, and eroded by an atmosphere thick as syrup. Shadows bent strangely by the haze. A horizon distorted by heat. And overhead, a sky not blue, not black, but an oppressive orange, like a permanent sunset smoldering across the whole planet. Those photographs, captured in the early 1980s, were the first and only color images humans have ever obtained from the surface of Venus. They showed a world that looks almost calm, eerily calm, until you remember the conditions. Temperatures that melt lead, pressures that crush steel, acid clouds drifting overhead. Venus crushed every probe we ever sent, but not before they showed us what hell looks like. Some Venera landers were warped as they touched down, their arms bent by the pressure. Others had their lenses cloud over, or their electronics fail as the heat overwhelmed their circuits. In one case, the lander accidentally dropped its soil sampler onto its own camera lens because the atmosphere distorted its mechanical arm. Even the equipment couldn't tell where anything was. No probe ever survived long enough to see a sunset. On Venus, machines die before evening comes. And as we reach the surface in our imagined descent, we can almost hear what the last moments of a Venera lander sounded like. A crackle, a hiss, a soft fading tone as the radio transmitter gives out. Then, silence. The kind of silence only a crushing world can impose. The Venera missions are still unmatched in their bravery. They revealed what no telescope ever could. They gave us a direct, intimate glimpse into a planet that punishes every attempt to touch it. But Venus still has secrets, and one of them shook the scientific world. Before it became a furnace, Venus might have been a world with oceans. That idea alone feels impossible after everything you've just passed through. The acid clouds, the crushing air, the molten heat. But the story of Venus runs deeper than its present-day hellscape. Long before the runaway greenhouse took hold, Venus may have looked surprisingly familiar, not comfortable, not green, not Earth-like in the way we imagine continents and rain, but warm, humid, and wrapped in gentle clouds that let sunlight through instead of trapping it. This idea isn't fantasy. It's built on decades of atmospheric modeling, geochemical clues, and one of the planet's most intriguing fingerprints: the ratio of deuterium to hydrogen in its atmosphere. Water molecules that escape into space leave behind heavier isotopes, and Venus has an elevated amount of deuterium. Something long ago evaporated. Something large enough that scientists believe Venus once held shallow oceans the size of the early Earth's seas. Picture it for a moment. Venus, 3 or 4 billion years ago, with thin clouds drifting across a sky that was bright but not lethal. Warm, not scorching. Perhaps with rain, maybe rarely, maybe gently, falling into shallow basins. A world with liquid water, mild winds, and temperatures that hovered in a range where chemistry could explore possibilities. A world not destined for life, perhaps, but a world where life wasn't unthinkable. But that world is gone now. Steam rose, oceans thinned, clouds grew thicker, heat built faster than the planet could release it, and one shift at a time, Venus crossed the tipping point that Earth avoided. It's the ultimate reminder that two planets can start nearly the same and still end galaxies apart in outcome. Then, in 2020, a discovery brought Venus back into the global spotlight: phosphine. A research team reported detecting this gas in Venus's upper clouds, a molecule that, on Earth, is almost exclusively produced by biology or by industrial chemistry. Since Venus has no factories, the claim sparked enormous excitement. Could microbes survive in the mild upper atmosphere, far above the deadly surface? Could something be swimming in droplets of acid, in a niche where pressure and temperature resemble the conditions at sea level on Earth? The scientific world debated immediately. Some researchers argued the data was too noisy. Others said the signal might be a misinterpretation, a telescope artifact, a processing error. But follow-up analyses hinted that something unusual might truly be there, even if it isn't phosphine. Some chemical signature persists in the Venusian clouds that we cannot fully explain. It isn't proof of life, not even close, but it is an open question. And in science, open questions are the sparks that ignite entire fields. Why does phosphine matter? Because on Earth, it doesn't survive long without something actively making it. Volcanoes don't produce it in large quantities. Lightning can't create enough of it. High-pressure chemistry only gets you so far. On this planet, phosphine means biology. So when scientists thought they saw it on Venus, it felt like a whisper from a world that seemed far too hostile to whisper anything at all. And yet, there is a place on Venus where life could theoretically exist. At about 50 to 60 kilometers above the surface, the atmosphere is surprisingly Earth-like. Pressure similar to sea level. Temperatures in a range life recognizes. There are still acids, still clouds, still difficulty, but also, intriguingly, a narrow band of habitability floating above the inferno. That's why some scientists imagine future floating cities one day, drifting in the Venusian sky. Human habitats carried by balloons, suspended in the calm, bright layers far above the chaos below. Venus makes you ask a simple but haunting question. What if Venus took just one wrong turn? What if Earth did too, but in the opposite direction? A little more sunlight, a little more carbon dioxide, a little less early cooling. And we could be the planet hidden under orange clouds, warning the universe what happens when a climate slips beyond its point of return. As we reflect on the gulf between Earth and Venus, the difference feels impossibly thin. A delicate atmospheric balance shaped the path of one sibling toward oceans and forests, and the other toward fire. Venus is not just a warning. It's a reminder of how thin the line is between paradise and disaster. But the story is not done. Venus is rising again as a frontier of exploration. NASA is preparing 2 missions, Da Vinci Plus and Veritas, to plunge into the atmosphere and map the surface with unprecedented detail. Europe's Envision mission aims to reveal the deeper geology. China and India have proposed missions of their own. For the first time in decades, Venus is becoming a destination again, a world we thought we understood, but no longer take for granted. And beneath those sulfuric clouds, Venus is still keeping secrets. Maybe about oceans. Maybe about chemistry we don't yet understand. Maybe about the thin edge between habitability and catastrophe. Its story isn't finished. If phosphine is truly there, something interesting is happening on Venus. But if Venus teaches us how things can go wrong, Earth shows what can go right. From space, Earth glows with a softness none of its siblings can match. A calm blue sphere wrapped in white clouds, touched with greens and browns, drifting through the dark like a lantern designed for life. After the furnace of Venus and the shattered metal scars of Mercury, Earth feels almost unreal. Gentle, balanced, peaceful, a world that breathes. In the family of the Tellurian planets, Earth sits in the middle. Not the eldest like Mercury, scorched and battered. Not the troubled twin like Venus, swallowed by its own atmosphere. Earth is the quiet middle child, the one that didn't get too close or stray too far. And that position, as simple as it sounds, became everything. Here, distance determines destiny. Earth orbits in a band astronomers call the Goldilocks zone. Not too hot, not too cold, just right. Far enough from the sun to avoid the runaway greenhouse that claimed Venus, close enough to escape the deep freeze of the outer solar system. It sits in the only place where liquid water can stay liquid for billions of years, not boiling away like it did on Venus, and not locked forever in ice like it is on distant moons. But distance is only the beginning. Earth has systems that protect life with quiet, continuous care. The magnetic field, generated by the churning molten metal at its core, wraps the planet in a shield that deflects the solar wind. Streams of charged particles that would otherwise strip the atmosphere bare. On Mercury, the sun tears atoms off the surface. On Earth, the magnetosphere stands in the way. Then there's the atmosphere itself, thick enough to hold warmth, thin enough to let heat escape. A delicate balance between greenhouse gases and cooling winds. A mixture of nitrogen and oxygen that supports breathing, weather, oceans, and forests. It's easy to take this air for granted, until you compare it to the acid clouds of Venus or the ghost-like exosphere of Mercury. And of course, there is water. Oceans covering 70% of the surface, rivers carving the land, ice caps that breathe with the seasons, lakes, rain, storms, mist, humidity, every form of water you can imagine, shaping every continent and coastline. On Earth, water behaves like an artist, carving and smoothing and writing new stories over old landscapes. The more you look at Earth from the outside, the more delicate it feels. Its success is not the result of a one miracle, but a long chain of them. The right tilt, the right moon, the right atmosphere, the right timing of volcanic outgassing, even the right amount of continental drift. Earth is not perfect, but statistically, it is astonishing. And humans have been trying to understand this planet for a very long time. Eratosthenes measured its circumference with nothing more than shadows and geometry. Copernicus reminded us that Earth is not the center of the universe. Galileo and Kepler refined its place in the cosmic clockwork. Each step pulled Earth out of myth and placed it into the physics of reality, a world that works not because it is favored, but because it is balanced. Earth isn't flawless. It has earthquakes, storms, extinctions, and shifting climates. But for everything that goes wrong, Earth still works. It still makes room for oceans, forests, continents, and creatures that adapt. It still produces mornings and evenings that you can walk through without a suit. It gives you breathable air, drinkable water, quiet nights, and warm sunlight. And compared to its siblings, that is rare. Among the 4 rocky siblings, Earth is the only one where you can walk outside and breathe. As you sit with that thought, the mood settles into calm appreciation. You're listening not just to astronomy, but to gratitude wrapped in scientific truth. You're on the one world that got everything right long enough for life to take hold. The one that didn't drift into fire or fall into silence. But the story of the rocky planets isn't finished. Earth may be the sibling that made it, but Mars is the one that almost did. Mars greets you with a cold red glow, soft, muted, almost shy. Not the violent brightness of Venus, not the scorched metal shimmer of Mercury. Mars shines like an ember that never quite became a flame. From far away, you can already feel the quiet nostalgia of a world that tried and came close, so close. Of all Earth's rocky siblings, Mars is the one that feels strangely familiar. Its day is just a little longer than yours, 24 hours and 37 minutes. It has seasons, tilted by an axis not so different from Earth's. Polar caps that grow and shrink, dust storms that sweep across continents, sunrise and sunset that, for a moment, look almost like home. And then the details begin to bloom. Look at the poles. Each cap is layered with water ice and frozen carbon dioxide, stacked like pages of a planetary diary. Spiral grooves swirl across the caps, patterns carved by the same Coriolis forces that twist hurricanes on Earth. They're beautiful in a quiet, mathematical way, shaped by winds thin enough to whisper and cold enough to bite. Move your eyes south, and the planet's landmarks rise like monuments in the desert. Olympus Mons, the tallest volcano in the solar system, looms 3 times higher than Everest. Its base is so wide that if you stood on the edge, the curve of the planet would hide the summit from view. It didn't erupt once or twice. It erupted again and again, slowly, over millions of years, building a mountain so massive that only Mars's low gravity could have allowed it. And then there is Valles Marineris, a canyon system so vast that if you placed it on Earth, it would stretch from New York to Los Angeles, up to 10 kilometers deep, 10 Grand Canyons stacked on top of each other. Its walls are scarred by landslides, fractures, ancient flows of rock and dust. It feels like looking into the ribs of a planet, exposed to the cold, thin air. These colossal structures exist because Mars is a planet frozen halfway through its ambitions. Its crust is thick and stiff, its gravity weak. Volcanoes can rise higher without collapsing under their own weight. Canyons can widen and deepen without the erosion that reshapes Earth. Mars builds big, and it keeps what it builds. But the most haunting part of Mars isn't its mountains or canyons. It's the memory of water. Real, flowing, persistent water. Across the ancient terrain, you can trace valleys carved by rivers, soft V-shaped channels that wind like forgotten pathways. There are dried deltas where water once slowed, spread out, and dropped sediment in patterns identical to river mouths on Earth. Minerals appear in the soil only when rock meets water. Clays, sulfates, carbonates. They whisper the same message. Mars was once warm and wet. For a time, millions of years, perhaps longer, Mars may have had lakes, shorelines, storms, clouds, rain, maybe even oceans in the northern lowlands. A climate mild enough for chemistry to dream of life. But Mars couldn't hold on. Not the way Earth did. Its magnetic field faded early, leaving the atmosphere exposed. Without that protective shield, the solar wind streamed in like a cosmic sandblaster, stripping gas away molecule by molecule. The air thinned, the pressure dropped, the water escaped. Some frozen into the soil, some locked in polar ice, some lost into space. Today, Mars is quiet. The sky is red with dust. The temperature hovers around 60 degrees C. The air is so thin, you'd need a pressure suit just to take a single breath. And yet, Mars still keeps its memories. Every valley is a photograph from a wetter past. Every mineral is a fossil of vanished rivers. Every canyon wall is a reminder that this world once held energy and warmth. Mars almost made it. It almost joined Earth in the narrow club of living planets. And that's why it feels so personal, so human. It tried, it reached, it changed, and in the end, it fell just short. Standing here in your imagination, surrounded by cold dust and ancient landscapes, you feel a surprising tenderness for this world. Not pity, just a quiet recognition. Mars is a ghost of a world that could have been. A reminder that the line between flourishing and fading is thinner than you think. And so, as the last sibling fades into the red twilight, you prepare to return to the one world that stayed gentle. Mars tells its story softly, then steps back, leaving you with gratitude for the planet you call home. 4 worlds, 4 fates. You let the words drift in slowly, like the first deep breath at the end of a long day. The story you've been traveling through begins to settle. Quiet, gentle, familiar, in a way only cosmic stories can be. These 4 rocky planets, born from the same swirling disk of dust and fire, now lie scattered across the inner solar system, like siblings who grew up and took 4 very different paths. You start with the eldest, Mercury, the small one made of metal and scars. A world scorched until it glowed, cracked until it folded, battered until the surface looked like shattered glass. A place once half melted under a young, angry sun. And yet Mercury survived. It grew a comet-like tail. It kept its strange orbit. It endured what no world should have had to endure. Then you drift to the second world, Venus, Earth's twin in size but opposite in fate, brightest in the night sky, wrapped in clouds that shine like polished pearl from afar. But inside those clouds, an atmosphere thick enough to crush steel, and a heat hot enough to melt lead. Venus, the sister that looked like Earth, until everything went wrong. A runaway greenhouse, a warning written in the sky, and then home, Earth, the quiet middle child that somehow got everything right. The one with oceans, clouds, soil, forests, wind, breath. The one protected by a magnetic field, strong enough to shield life, but gentle enough to let sunlight through. The one that sits in the narrow Goldilocks band, not too hot, not too cold. The one where you can step outside, fill your lungs, and simply exist. Earth is the sibling that remained soft, the one that held on to balance. And finally, Mars. Red, dry, silent. A world that almost joined Earth in the realm of living planets. Mars had rivers once, lakes, storms, clouds. It built mountains taller than anything Earth ever could. It carved canyons deeper than imagination. But Mars lost its protection, its air, its warmth. Today, it is a memory frozen in dust, a ghost of a world that almost made it. 4 siblings. One burned, one drowned in heat, one flourished, one faded. They were born together, circling the same star, shaped by the same physics, yet destiny pulled them in 4 directions. Their lives, because in a cosmic sense, planets have lives, remind you how delicate everything is. How a few degrees, a bit of atmosphere, a magnetic field barely stronger than a fridge magnet, can decide everything. You breathe slowly now, letting the thought settle, letting the night deepen, letting the voice in your ear soften its pace, dropping to something closer to a whisper, steady and warm. The universe is vast, complicated, unpredictable. But your world, your sibling in this family of 4, is gentle tonight. Outside your window, Earth still turns quietly. Clouds drift, oceans breathe, fields cool under the stars. Nothing is demanding your attention. Nothing is rushing you. You are on the soft one, the safe one, the lucky one. And as these 4 worlds drift through the dark, each following the path written for them billions of years ago, you get to rest on the quiet one, the one that balances fire and ice, chaos and calm, possibility and stability. This family of worlds will always be out there, turning slowly in the endless black. And there will always be more to explore, more to wonder about, more stories waiting for you when the night is long and your mind needs a place to wander. But not right now. Right now, you can let the journey end. You can let the planets fade into soft silhouettes. You can let your breath fall into a calm, easy rhythm. You can let your thoughts drift like dust in sunlight. You're safe. You're home. You're on the gentle one. We'll explore again next time. For now, good night, traveler.